Lecture 3 already, and the final one that lays foundation for the rest of machine learning that is coming. We will today look in detail into how can we assess the quality of a model, how good is it, and as a next step what we usually want to do, how can we select which model we finally want to use. We have 3 steps. We will, I think, take some time on how do we deal with the data, how can we make the most out of the data that we have for training, for evaluation, for all the purposes. And then we will look, okay, what measures exist, what figures of merit exist in order to assess a model. And finally we will look, okay, given that we have made the best out of our data, that we have measured how well we are doing, which of the models do we take? There's a lot of additional material in the appendix that will not fit into a 90-minute lecture. You can use that just for your reference. If you're interested in certain topics, there are pointers to the appendix where you can have basically a one-pager on certain things with pointers to the literature where you can read more on it. So take that as a reference for when you're doing machine learning in the future. You need certain measures, you want to assess a specific method, just have a look here, you will find probably some pointers where you find the specific stuff. Goals for today. There's one important concept in machine learning. It is a little bit debated, also what it means is debated. It's anyway an important concept, and that's the concept of the bias variance trade-off. So if you just remember one thing, remember what is meant by the bias variance trade-off. The second most important thing is know how and why you use your data wisely. The data that you have, the label data. Fine, let's dive into the topic. How can we handle the data to train our model and to evaluate our model? This is basically the attempt to find an answer for these 2 questions. How to learn and evaluate algorithms based on just limited data. We wouldn't need to talk about that if we would have unlimited data. But we just have limited amount, so it's somehow wise to think about how can we make the best out of it. And how to deduce the true error that we cannot measure by definition based on that limited data set, that limited sample. Get out of training. So we try to answer these 2 questions. I want to give you an explanation of that figure here. It's taken from the scikit-learn library, and I think it drives home a very important point, and that is, even if machine learning methods have quite some similarities in what is the reasoning behind it, the models that come out of them are completely different. And this illustrates it in a perfect way, I think. Imagine this. Here are 3 different data sets. You see training and test points. I think the training points are more solid, and the test data points a little bit more shadowed. 2 classes, red and blue, and we see here different models and how the decision surface looks like that these models build based on this training data. So basically, what we see here, the colored surfaces, are the regions of these 2-dimensional space, and if there would be a point here, it would have been assigned the red class by this method. And if a point would lie here, it would have been assigned the blue class. And in the lighter colors, the model is not so sure, but it would say. So these are all machine learning methods. These are very simple data sets. The models all look completely different. And you see here small numbers. This is the accuracy on the test set. So 97%, 97%, 97%. Where's another 97? 97%. 1, 2, 3, 4 models that have exactly numerically the same test set error, and they look completely different. They learn complete different concepts. That is not super profound, but I think if you see it, that just opens up your you're thinking about what does machine learning really do. It learns completely different things, and from the figures of merit, this accuracy thing here, you would say, oh, they're all equal, I can take any of these, but they learn different things. Look at this one, radial basis function support vector machine, we will talk about that next week, and the linear support vector machine. Completely different concepts, exactly the same score. So this is why we have this lecture today. We talk about how can we assess these differences and how can we choose which one we take. If we just base it on this number, we have not much to choose. Maybe we need different numbers. So that's really an important choice we take. So, what is model assessment? Model assessment actually means we evaluate the model we have built in order to have an idea how good they are. What's the performance in terms of quality, accuracy, or whatever. We talk about later what we measure. And model selection is then, which one do I take? Or do we take them all? We'll talk about that in 2 weeks. So, maybe that's one of the 2 most important slides for today. And I guess you all know all of this already. We will just go over it that needs to sink into our minds as machine learning developers. We have our data, the precious data, the data that was very costly to get and to label, and now we want to do something with it. We want to train a model. We do want to do machine learning. First thing we do is we take test set apart. What do we do with the test set? We lock it away. The test set is not the thing you use to do your hyperparameter tuning. And to say, I tried this model and this model and this model and play around with it for half a year and then I report which one is best. That's not what you do on the test set. The test set is the thing that you lock away, don't touch for the whole duration of the project. At the very end, when you are sure that this is the model you want to go with, you evaluate ideally once on the test set, note down the score and show it to your project owner and say, this is what we achieved. Of course you can, this is a little bit overdone, you can use it maybe more than once, but that's the idea. This is not the thing you develop on. You take it away. You use it very, very rarely. Why? Because if you test often on this one, knowledge will leak from here into your training set. Not because data is somehow leaking, but because you see the performance in this and you take these thoughts to training. And it will leak by means of your own mind. And you don't want to have that. Otherwise, whatever you measure on this will be optimistically biased and you have no clue how well you're doing in practice. So you have to lock that away. And that's a problem because data is costly and so valuable. And now you have less data for training. And we heard the more data we have, the better the model will be. And so it's unfortunate that we have to take something away. And if we have to take that away, we still need something we can often test on while developing. So yeah, we still need a validation set. So we need some data for training. Then we need to see how well the training is doing, fiddling around with all the parameters. And in the end, we have to use the final test set. That means for the real training, we only have about 60% of the data. Even if we go down here from our original assumption of, let's lay aside 30%. And really the problem is a trade-off. The more data we have here, the better the estimated model will be. The more data we have here and here, the closer to the real truth the measured error will be. So we cannot just go down here to very, very few. What do we do now? Thank God there are statistics. And there's a very cool thing called cross-validation. Who already knows cross-validation? 70%. Nice. I talked to the 30% now. What is cross-validation? You take all the data you have during development time. Like, let's take aside the test data for a while instead. And now we do the following. K times, let's say 5 times. We train on 1, 2, 4 of the 5 chunks of data, and we evaluate on the remaining one. Then we switch the remaining one. We train again on 4 chunks of the data, we test on the 5th. We switch the chunks, we train on 4 of them, we test on the 5th. We do that 5 times. what do we gain? We test successively on all our data, and we train successively on all our data. And we get different measurements of the error. So we somehow see, are they all in the same region? Do they vary a lot? We get a much better estimate of how sure can we be of the error. It's a really nice thing. In practice, you should do it between 5 and 10 times. Ideal is 10 times. That's what practitioners say. Of course, the downside is you train 10 times, you evaluate 10 times. 10 times as computationally costly as when you just do it once. So normally you should do cross-validation always. Because of computational constraints, you can go back to the old setup of having a training and a validation test. But ideally you do this. At least for, let's say, shallow machine learning, where the training time usually is not in the range of days or weeks. In deep learning, somehow this came a little bit out of favor because training already takes weeks. And if you do it 10 times, then the turnaround is a little bad. I actually talked to my statistics colleagues, and they told me you can actually do this. You don't need a separate test set if you do cross-validation thoroughly, and thoroughly means cross-validation is actually the outer loop around every optimization that is taking place. Like around every fiddling around with a parameter, around every playing around with your architecture or whatever. If cross-validation is the outer loop around everything, you don't need a separate test set. You can just use that, report the scores, like the mean and the standard deviation of your errors, and you don't need a separate test set. Makes by far the most of your data. But most people don't understand statistics, so most people will think this is fishy. So if you don't want to have to argue with the guy who pays you, if it's not a statistician, go back to this one. You can do this. Okay. Questions or remarks from your side up to here? Yes?
If you repeat it 5 times, do you always have a completely new start, or do you keep the learning data from the old repetitions?
You would start really from scratch.
From scratch.
Yeah. You divide your data into, I think here it's 10, so let's say into 10 folds or 10 bins. You take 9 of them, train on it completely from scratch.
Okay.
Test on the remaining one. Then take other 9, like take this for evaluation and so forth. But you would basically do in all the folds from scratch, whatever that means. In deep learning, you often start with transfer learning from some model. Of course, you can also do that, but you don't learn from the previous cross-validation ones. Okay. Normally, they are independent, so you have an independent error measurement. Okay. Good. Let's talk about different sorts of errors. There is, and this is what we are usually interested in, the true error. The true error is the error that our model would have on the whole distribution of data we could apply it to. Meaning all the data in the universe, and that is mathematically valid. Of course, we cannot observe this error. We don't know it. We can only estimate it, and we have to estimate it from the sample of data we have. Of course, we can enlarge our sample of data, but even if you collect all the data on Earth, that's probably still not the whole distribution, just a very good fit to it, hopefully. So what we actually see is the empirical error, or the so-called test error, the one that we calculate on our test data. And throughout that course, when we are not specifically talking about division of training, test, and validation set, probably test set could always mean test or validation set, depending on are you at the end of your project and finally test, or are you still developing, and then this is the validation error, of course. So it means error on a data set that wasn't used for training. That's the empirical error is measured over a specific sample from the distribution you could apply normally to. And that means it's just an estimation of the true error. It's not the true error itself. This error will have some variance. If you test on another sample, the error will slightly be different. hopefully in the same region, but it can vary a little. And it will vary less if we give it more data to evaluate it. So that's the thing we usually observe to get a feeling for this. Of course, we can also observe the training data. The error on the data we actually gave to the algorithm to learn it. I extracted through because you can just directly forget about it. It's nothing we should measure. It has nothing to say. It's, at least when we are interested in this doesn't tell us anything, but a hopefully optimistic number that doesn't tell us anything about the performance of the model. For some machine learning approaches, you do that to see does training converge. You do it, for example, for neural networks. That's okay. This is not what is meant here. But some people do report training errors as a proxy for the true error. That doesn't work. You can ignore it. If you showed, that would basically be the same thing than giving you the final exam plus the correct answers a week before the final exam, and then giving you that exam and taking that as a sample of the quality of the class. That's an assessment of the quality of how well you can remember what you read before. Yeah. So, same here. How good is our estimate? Usually, when we collect data for machine learning, we don't look for a training and testing set completely separate. We don't send two people away and say, you collect training data and you collect evaluation data. We collect data in one go or several goes, and then we divide them somehow arbitrarily into a training, test, and validation set. So the testing set and the training set are not independent statistically of each other. That means the test error is optimistically biased. We should assume that the true error is higher than our test error. Why? Because the test error has more resemblance with the training data than with any new data chosen from the distribution peak. So, test error is optimistically biased. And the test error has a higher variance. It varies. If I calculate it over a different data set, I will get a different one. Oh, that's a bad thing. We have only an estimate of the thing we're interested in, and it is biased, and it has a high variance. If we are interested in how much does it vary, how big is the bias, you have to look into confidence intervals. There is, I think, yes, a slide in the appendix how you can calculate confidence intervals for the errors you measure. There's a very nice chapter on that in the book by Mitchell that explains it very well and gives you all the formulas and tables how to really do it. So if you are somehow obliged to report confidence intervals for errors you report, have a look at this appendix slide. It really gives you the, let's say, the recipe how to do it. Without all the other things you could also know about confidence intervals that don't play a role here. Usually, we don't need to do that. That's a thing for academic research. If you're reporting errors in a research paper and you want to claim that your method is better than state of the art, and you're very close to the state of the art, you probably have to say, is it significant? How much better am I? And then we need confidence intervals. Sources of errors. Where does the error come from in the first place? And this is maybe the second most important slide today, because it starts introducing the so-called bias variance trade-off. Basically, when our machine learning model is committing an error, the error can stem from different things. For example, we choose some hypothesis space from which we draw or learn our function, right? We talked about that in lecture 1. We saw an example of it last lecture. If we assume, for example, that the hypothesis space is a space of linear functions, we can almost always say that the hypothesis, the best hypothesis we find, will be at some distance of the true function, because almost nothing in the real world is really linear. There are always some small fluctuations, even if it looks almost linear. So the assumption we make by choosing a specific hypothesis space usually means that the thing we will learn can only be so and so close to the true thing. That's one source of error. We could call that a bias. It's a systematic error. We made it systematically by making a specific choice of what kind of function do we want to learn. It's systematically aiming next to the goal. Then, our error depends on which exact data set did you use for training and for validation. If you would train on another sample of the real data, probably it would come out a little different. Maybe not too different, hopefully not too different. In the end, we still want to generalize, but it will come out a little different. Because different samples give different information in the end. We could call this kind of error a variance. It depends on the data. When we use other data, it will look a little different. And then in the end, at least in the real world, we usually have some uncertainty in the process that cannot be explained, that is just there, maybe because our measurements of the samples are not very exact. Our sensors have a certain noise on them. For example, if we're measuring audio data, we usually have an audible noise, Rauschen, on it. If we measure other kinds of things, we basically have the same thing, and we still call it noise. So in the end, our final error consists of 3 parts. And this is also in the mathematical sense completely true as it is written here in case of the mean squared error measurement. So if you measure mean squared error like we did last lecture, then this equation is exactly true. Our mean squared error is the sum of all the parts of the error that are here due to bias, a systematic being off of the true function, of variance, a sensitivity to the choice of samples we use for training and for evaluation, and the irreducible error, or so-called base rate, that is just the noise in the system. And they are just added together and make up our whole error. So when in the end, we are interested in reducing the error. We want to have a machine learning model that works very well. So how can we do that? This equation basically shows us there are 3 components. If you want to get the whole sum down, we can focus on all of them or just one of them. It somehow helps us to understand how can we reduce error. What could we do? For example, we could try to get the irreducible error down. But as the word says, that's maybe not the best idea. It's irreducible. We cannot do anything about this, usually, except we get better measurements and get rid of noise. So we cannot do anything about this. So we have to cope with bias and variance, or systematically being off, and the variance introduced into the system by choosing a different sample. So how do these two relate to each other? There's a very interesting figure in the Introduction to Statistical Learning book. I think a similar one is in the Elements of Statistical Learning book, that you can read the following way. We have here, the y-axis is a measurement of error. So the higher, the more error we have here. Right. And here on the x-axis, we have a measure of the complexity of our current machine learning method. Think about it like, is it a linear function to fit our data points, like we programmed last week, or can it have curves in it? Is it a polynomial function or whatever that can more easily fit the different points in our data set? This is a measure of how complex can the function be, how well can it fit to the data points. And you see here, if our function, our machine learning model that we want to train, has a very low flexibility, for example, a linear model, then usually the variance error is quite low, while the part of the error that is due to bias is quite high. An inflexible model, by definition, has a high assumption on what do we expect in the data, and if this does not fit exactly, it will not work. So it has a high part of the errors due to the inflexible model just not being flexible enough. This is why the bias error is quite high. An inflexible model will commit a lot of errors independent of the exact data points it is measured on, because it will be off anyway. So the variance is quite low for inflexible models. If you have a much more flexible model, let's say convolutional neural network of current state-of-the-art, 200 million parameters, quite flexible. It has a very low bias. It's not systematically off. It can in the end learn anything. But if you give it a couple of other data points, it will learn a different thing, because it learns what you give it, and it has a capacity to do that. So a very flexible model has a low part of its overall error due to being systematically off, due to bias, and the high part is due to it has a high variance. In the end, this is a combined error. And you see here that there's usually somewhere a sweet spot between a model that is very inflexible and a model that is very, very flexible. That of course varies with the task you have. It means you have to find a model of fitting flexibility for the task at hand. Because you can basically try to get rid of that peak in the bias, or of that peak in the variance. You cannot get rid altogether of both. The only chance you have to lower the error completely, to get rid of the trade-off between bias and variance, in the end is, and I think it's somewhere here, to get more data into the system. Andrew Ng said it just in a second. Andrew Ng has a very nice quote appealing to deep learning, where he said, the only thing that makes really sense is take a very flexible model and throw big data on it. So take a very big neural network and use a lot of data. And that will get the whole error completely down. If you have big data, and if your data works well with neural networks, that's probably a good way to go, but not always we are in that regime. So we have to think a little more about the things. Yes.
How would you measure model flexibility? Can you even?
How would you measure model flexibility? There's not a very generic measure for it, but for example, if you, I think you can capture it quite intuitively. If your task is really regression, and you have some data points here, and we see somehow there's a relationship, the more we have here, the more we also have here, it probably could be modeled as linear. Something like that would be a very inflexible model. Something like that is maybe already more flexible. And okay, something like that is even more flexible. You see, this is somehow the wiggliness of that curve. This is something that is measured by VC dimension, by the way. But in that case, you could think these are all instances of a polynomial model where you vary the degree of the polynomial. If you set the degree of the polynomial function to 0, then you just have the linear function. If you set it to 1, if you set it to 1, you have the linear function. If you set it to 2, you have basically the parabol, the quadratic function. And this here could be a polynomial of order 5, degree 5 or something like this. So usually in all your models, there is somewhere a parameter which you can tweak and which controls the flexibility. In neural networks, it's the number of units you have and connections, basically the number of weights. The more weights you have, the more flexible the thing is, because it can learn more. That's the capacity of the model. We will talk a little more about that next week when we discuss support vector machines that have specific kernels that pertain to more or less flexibility. But usually in all these methods, you have somewhere a knob you can twist which controls how flexible it is. But they usually have different names and also different detailed meanings. Does that help?
Yeah.
Cool. More questions to that thing? we will see a little bit more about the bias variance trade-off and how we can exploit it to debug models in lecture V06. There you learn a concept called learning curves that uses this to basically show you, do you have a bias or a variance problem, or on which one should you work. So we will come back to that later. Okay, that was the foundation. We now know how we make up the most of our data, ideally by using cross-validation. And we know that we also need data for evaluation because the error varies again. Yes?
If we have some amount of data we can use to train and to test our model. So what percentage of this data do we use for tests and which for training?
Well, usually one set use 70 for training and 30 for testing, but then you don't have a validation set, so the usual split there is 60, 20, 20. But that comes from, let's say, shallow learning where you have not gigabytes of training data, not thousands of data points. If we are talking about like really, really huge data sets, you usually don't go to percentages. If you have, I don't know, ImageNet with millions of images, you usually reserve a couple of thousands for testing. You look that all the classes you want to have included are in there and so on. But then you do basically, you just reserve a couple of thousands for testing because that's enough and train on the rest.
So you can go below this 30%.
Yeah, exactly. So this is from with a setting in mind where you have a couple of hundreds, a couple of thousands, tens of thousands of data points for overall. And then this somehow makes sense. If you have plenty of data already, you don't have to grow that beyond a certain size.
But never use the test data for training.
And never use it for validation either. Like really lock it away. You need some data you can finally evaluate your model on without that you ever use it in the development process. I think that's important. It's not just that it is not input into the training process. If you had a look at it, you see certain things in it and you know, that's in the test set, so I have to take care for a new model, and bam, it has to leave. So, for example, if you have a project with a different unit or a different customer or whatever, what you can usually do is tell the customer in the beginning, like, don't give us all the data, reserve some for yourself. Then you're not tempted to peek at it.
But in optimization, in midterm heuristics, you exactly do that. You look at the problem and then you tweak your optimization thing to make the best. And
partly you do it here as well because your problem is deemed to be in all that. And both sets are thought to come from an overarching distribution. And usually you choose that at random. So what you assume that both are a sample of the same underlying distribution. That still holds true. So then you basically show a part of the problem from which you assume it contains everything. You show to the thing to tweak it, but you need independent evaluation, otherwise you have no idea how well it will do. Maybe that's a little bit different to standard optimization. Because we are purely driven by empiricism in machine learning, we have very few fundamental principles, and it's lots of empiricism. We try and we show empirically how well it works. We need to really take care for that we do that in a good way. That the numbers we report can really be relied on. And this lecture today is basically how do we do that. And first thing is, take the test data away, don't peek at it. Okay? Funny thing. A fundamental mismatch between students and lecturers usually is if you supervise the thesis of a student and the student comes and says, oh, I have perfect results, 100% accuracy. Usually the student thinks he has found something very interesting. And usually the lecturer thinks something from here went into here. That's 99% sure that's an error, and usually it is. So as soon as you gain some experience with that kind of stuff, you really see why it's so important to carefully evaluate, and therefore you have to take that. Okay, I repeated myself, I think, at least 20 times. So I massaged it into your way of thinking, hopefully. So let's look at what can we measure. Is it just accuracy or are there other things? And yes, there are other things. It has a little bit an encyclopedic character in the next couple of slides, so I won't go into lots of detail. It's more like I show you the big things and you can come back to that if you need it and take the form. Or you can ask if you're interested. So, I think we had that example at the very beginning of the lecture, of the course. Accuracy is not, it doesn't tell the full story. If you're in the business of having security cameras at an airport and you want to spot certain people that you don't want to have there because they're deemed to be terrorists, there are like way more people that are not in your database than the few that are. Meaning your classifier will be very, very, very accurate, even if it just says not a terrorist for everyone without regarding the data at all. But accuracy will still be way beyond 99%. So this measure, accuracy, the number of errors you commit given the total amount of things you evaluate, is not in all cases a very good measure. Because it's only a good measure if the different classes are balanced. You can have a certain, actually, you usually can commit two types of errors. And you see that if you measure, or you count what you do in a thing called a contingency table. A contingency table shows you your different classes you have in your data set and the different things you said, like you predicted. And then you just count how many of those that are really of class 1, the positive class, I predicted as positive. These are your true positives. And of course, there are also true negatives. These are the ones that are really negative and you predicted negative. Then you can have two types of errors. You can miss a positive one. It's called a type 2 error, a false negative. It is actually positive, but you predicted negative. So it's you predicted negative and that is false. And you can have a different kind of error, a so-called false alarm. You predict something as positive and actually it's negative. Usually, you should model it that way. Oh, nice. Maybe we can switch that off. Maybe we just leave it. Usually you should model it in a way that the class you're most interested in is your positive class, whatever that means. If you're interested in detecting some kind of cancer, even if that sounds a little bit morbid to call the cancer positive, but then your cancer class is a positive class. Because you measure errors from there on. Also, if you want to detect terrorists, your terrorist is a positive class. So positive is usually the rarer class, if there's a mismatch. And from that thinking here, it is called a false alarm if you report something as positive that actually is not. I think we should really switch it off. Excuse me. I should do that before. Okay. If we have counted what we predicted in that sort of contingency table, and that very easily extends to multi-class cases as well, so you can have as many classes as you want, not just two. Then you can calculate a lot of different error measures based on the numbers in the table that give you a different view on how well are you doing. Accuracy is one of the measures you could have, but it's not the only one. Let's have a look. Okay. So accuracy would just be you count the two cells of your table where you were right with your prediction and divide by the sum of all the cells in the table. That's accuracy. That's easy. But there are a lot of other things. Kappa statistic, for example, is very interesting if you have different predictors and you want to see how often do they agree. That's not too interesting if your predictors are machine learning algorithms. It's very interesting when your predictors are human neighbors, like people who did the ground truth labeling. Funny story for that, I once was part of a research project where we automatically tried to classify scenes from people playing a first-person shooter game, and we wanted to predict per frame is there violence in that scene or not. Of course, in first-person shooters, you sometimes have blood and gore and whatever going around, and we wanted to predict in these frames is there violence or not. The background of the research project was it was together with psychologists, and they attached some measurement stuff, EEG and so, no, how do you call it? Is it EEG, the brain functionality measurements things? They measured all these kind of physiological signals while the people were playing. They wanted to find out, is there something specifically going on in these persons where they are simulating violence, and is it somehow similar to real violence? As far as I remember, it was not too similar. But anyway, in order to make that correlation, we needed to label hundreds of hours of videos of people playing, I think, Counter-Strike or something like that, if there is violence in the scene or not. And actually, we were not too impressed with our classifier. It worked somehow, but I think it worked like accuracy 80% or something like that. And it should be easy. If there's red on the screen, then it's probably, or the camera is going dead, then you're probably dead and there was violence. But just 80%. And we were not very happy with our results until we saw the kappa statistic of the human annotators. We had some students paid for watching their videos and just pressing the button as long as there was violence in the video. And their inter-rater agreement was below 80%. So actually our algorithm, while not doing very well, was still doing better than the humans. So we were a little bit more pleased with our results afterwards. Very interesting measures that are reported in a lot of different fields that have to do with machine learning, even if they come from information retrieval, are recall and precision. Who is familiar with recall and precision? Okay, the rest of you should become familiar with it because it's really important. Why? Because this one really gets a trade-off between the two kinds of errors. And it would also not say, like, it helps you in the case of the terrorist example, where you classify it as 99% correct, accurate, even if it doesn't classify a single terrorist. Recall and precision will show you the full picture here. They basically have a trade-off between themselves. And we will talk about it in a second a little bit more. F measure is just the one number, a scalar combination of recall and precision. It's a so-called harmonic mean. As Andrew says it, you need always one measure, one figure of merit, a scalar number that you can plot to see how well your project is doing. You should ideally measure much more things and record them all, and later for your publication or whatever, see which one tells the story best and which one is most informative, but you need one thing you observe usually during development. And if you're going for recall and precision, these are two. Bad. So there's the F measure that combines them into one, and only if you're doing good on both classes, in all classes, then the F measure will go up. If you are in the medical domain, you will usually hear a lot about sensitivity and specificity. It's basically a similar thing than recall and precision. It's just defined a little bit differently. But it also captures the trade-off between the different kinds of errors. And in the end, what was recall? What does recall say? Recall tells you how many of the positive things did I predict as positive. And precision tells you how many of the things I predicted as positive are actually positive. So one tells you how much of the things I want to report I actually reported. How much did I find? It originally comes from information retrieval. Precision tells you from all the things you gave me as relevant, how much of it actually was relevant. And you can very well adapt it to classification and even to clustering settings. So, of course, there are two naive ways to push either measure. If you want to have a recall of 1, like the highest possible recall, 100% recall, you just predict everything as positive. You just return everything. Right? Then you have recall at 1. And you can also make precision 1 or 100%, very easily by not reporting anything. Then you don't commit any error by reporting something as positive that is not there. You have a recall of 100%. But not a very good result. And of course, you can imagine that between these two extremes, there is somehow again some space that you can navigate by fiddling around with, in the end, one parameter of your algorithm that tells the system how strict is it. If it thinks something could be positive, from which point on it says, yeah, that's positive, I report it. Or no, that's not positive, I don't report it. If you fiddle around with that strictness parameter, whatever it is, it's a little bit like the flexibility parameter that is not there explicitly in some ways, but usually you have something like that. Usually you also have such a strictness parameter, a threshold, for example. If you want to see how well overall is my system doing, regardless of where exactly I define the threshold to be the operating point, you usually don't look at specific recall and precision measures, but you look at a curve, a recall precision curve, or so-called receiver operating characteristic. Then you can look at, okay, how is that curve shaped? That is what we look at in the next slide. So there are a couple of different curves you can calculate that show you the whole picture. How well is our classifier doing regardless of how strict I have set it? It shows you all the points it can operate on. From 100% false positives to 0 false positives. From 100% true positives to 0% true positives. Or if you prefer, on a recall precision axis. And here you see a very bad classifier usually is here on the linear axis. The farther you go up in that direction towards true positives very high and false positives very low, the better your classifier is. So if you don't want to just report a specific number on that curve, but basically the whole story, what is your classifier capable of, what you do is you create the whole curve and you calculate the area under the curve. And this is a very important measure that you read often in papers, abbreviated as, let's go back one slide, AUC, area under curve. This is usually, you create a rock curve and you measure the area. A better classifier will have a larger area under the curve because this point will go up here. And the same is to some sense true for the recall precision. So if you want to make a full assessment of the method you have there, usually what will be expected from you is a rock curve. Rock curves, just to go very, very little bit into detail, have their origin, as far as I know, in electronics and specifically in radar systems. So they were developed to assess the performance of radar systems in a military setting. I think in the 50s, around that time. So engineers then wanted to see what is the hit rate, like there is really something going on in the real world and it shows up in the radar. Where is the false alarm rate? My radar is showing some points like an airplane, a ship, whatever, and actually there's nothing there. So it plotted this thing called hit rate, true positives, versus the false alarm rate. This is how these axes were motivated. How do you construct it? You build your model, you somewhere have your strictness parameter, your threshold, when do I report something? Imagine that your model, for example, gives out a probability of how probable is that what you have seen here is a hit. And then your strictness parameter is just a threshold. At what probability do I say, okay, it's really a hit? If you set it very low at 0%, everything will be a hit and you have lots of false positives. If you set it very high, you will have less false positives, but probably also less true positives. This is how you construct the curve. Actually, by the way it looks like, if it is a jagged curve like that with rectangular steps in it, this basically means that, where is it? you just had one set of test data, and you always test it on the same set. If the curve is very smooth, it shows that people applied cross-validation. Good. Why is it a bad idea to do that? I mean, I told you lots of reasons why it's a good idea to make a raw curve to assess your performance of a classifier. Why is it a bad idea? Could it be a bad idea? Takes again a lot of additional time. You not just train one classifier, you probably have to do more. If your strictest parameter happens to apply during training, and even if it only applies during testing, you have to test a lot of times. So it just takes time. It's an outer loop around your evaluation stuff. Let's make a break and see you again in a couple of minutes.